Okay, so we had just talked about the integrated rate laws and half-lives of second order and first order reactions. There's also, by the way, an equation for zero order reactions that is on your periodic table and equation sheet. You would use it the same way as you would use the first and second order reactions, but it is pretty straightforward. And we won't see much of that in our class, so that's why I don't have a slide on it. But let's start with this learning check. So we are told the rate constant for a first order reaction where you have reagent A and that just forms some products is that value at 150 degrees Celsius. And then they give you the concentration of A at the start of the reaction, and the question is, what is the concentration of A after 2 seconds? So we've learned a lot of equations in our class, and one of the big skills that you should develop, and you will develop, is how to determine which equation to use for which question. So a few important things that we are told here is that this is a first order reaction, so we need to use an equation for first order reactions. We have been given rate constant, so we don't need to find that. We have K. And then we're given initial concentration, and we're asked for the concentration after some time. So when time is a factor here, and they are not talking about half-life, then we will use the integrated rate law. We need to use the one for first order reaction. So that is the natural log of A at time t divided by, let's use the y equals mx plus b version. That's the version that is on your periodic table and equation sheet. So that will be natural log of A at time t is equal to negative kt plus natural log of initial concentration. So we'll plug in everything that we can. We don't know concentration of A at time t, that's what we're looking for. We have K. We have T, that is 2 seconds. And then natural log of initial concentration. This is negative 1.38 minus 0.174. So natural log of A at time t is equal to negative 1.554. To remove the natural log part of the equation, we need to raise e to the power of both sides. So if we do e to the natural log of A at times t, that just cancels out the natural log. And then we'll do e to the negative 1.554. And then this will give us concentration of A at time t is equal to 0.211 molar. So the math here is pretty straightforward. It's really just being able to determine which equation to use and then what every value that you're given actually tells you. So then I have this follow-up question. What if the reaction was second order? If the reaction is second order, then we need the second order integrated rate law. That is 1 over concentration of A at time t, which is equal to KT, plus 1 over initial concentration. Then you would plug in values again, and you would be able to find concentration of A at time t at 2 seconds is 0.389 molar. These are questions where it may be helpful to also think conceptually. We start with a concentration of 0.840. Concentration of the reactant after some time should be lower, so you can just double check that your concentration at time t is lower than your concentration, or than your initial concentration. Okay, going to the next learning check, we again have a first order reaction, and then now I see we're asked about half-life. Well, we're given the half-life actually, so it's 63.4 minutes at 225 degrees Celsius. So here is T 1/2. We are looking for the rate constant K, and then we'll determine the percentage of reactant remaining after 25 minutes. So, a couple of steps here. Let's start with part A. Because we are given half-life, if we go back to the first order equation for half-life, half-life is equal to natural log of 2 over K. So finding K is actually pretty easy. K is equal to the natural log of 2 divided by the half-life. So that's natural log of 2 over 63.4 min. So K is 0.0109 minutes to the negative first power. All right, so we've got question A done. Question B, now when you're asked for a percentage, you don't have to necessarily find the exact amount, and we can't because we don't have the initial concentration. So we wouldn't be able to use the initial concentration, K, to find the the amount of reactant remaining after 25 minutes. When you're asked for a percentage or a ratio, oftentimes you'll use an equation that has those values that you're looking for in a fraction. So here's what we'll use, and that is the concentration of A at time t divided by the initial concentration. So a little note to write here at the top. Let's say you start with 100 molar of A, so that's your initial concentration. After 25 minutes, there's 50 molar. Then the amount remaining would be the ratio of those two, the concentration of A at time t divided by initial times 100%. So this is the percent remaining after a certain amount of time. The integrated rate law for first order reactions has that ratio built in where we have the ratio of concentration of A at time t divided by initial concentration. This is equal to negative K times T. So all we need to do is actually solve for that ratio. We don't need the actual, and we can't find the actual value of A at time t and 0 because we don't have any information about concentration. So plugging in values, we just calculated K. And then time is 25.0 minutes. Okay, so we have the natural log of this fraction, the ratio of what's remaining over initial, equal to that negative 0.2733. Raise both or raise e to the power of both sides, we get this fraction, or this ratio, we can say, is equal to e to the negative 0.2733. This is 0.761. If we multiply that by 100%, then we have 76.1% remaining. Okay, so again, just solving for this ratio, and that you can use to determine percent remaining. Okay, we will move on to the next section, but just a reminder, main learning goals from this section is being able to use these equations, the integrated rate laws and half-life equations, to solve related problems. Okay, so next we're going to talk about reaction rates and temperatures, and then we'll talk about activation energy and what that is more explicitly. So far we have learned just briefly that increasing temperature increases the rate of a chemical reaction, or at least that it affects the rate of the reaction. That was very quickly summarized in 14.1. We also know that rate constants are temperature dependent. So if a reaction happens at a different temperature, the rate constant will be different. So now we're going to understand why increasing temperature increases reaction rate, learn about other factors that determine the magnitude of the rate constant. So activation energy, collision frequency, and collision orientation. Okay, so for all reactions, energy is required for the reaction to begin. This is a reaction coordinate diagram. We have reaction progress on the x-axis and potential energy on the y-axis. Reactants always start at some energy. Then energy is required to get to this transition state. And then the products could be higher energy than the reactants. That would be an endothermic reaction. Or they could be lower energy than the reactants, and that would be exothermic. So this is a general diagram just to show those key features. The energy between the start of the reaction, so the reactant's energy, and the highest energy point, the transition state, that is activation energy. Oops. So the energy required to reach the transition state is E subscript A, or activation energy. And then another note is that the transition state here, this is always higher energy than reactants and products. Doesn't matter if you have an endo or exothermic reaction, the transition state is a high energy state. It's always higher energy than reactants and products, and so the activation energy is energy required to get there. So reactants need to absorb enough energy to get to the transition state, and then it's like a roller coaster. Once you're up there, it's easy to continue the reaction and reach the products. Here's an example of an actual reaction coordinate diagram where 2 moles of NO, nitrogen monoxide, forms 1 mole of N2 and 1 mole of O2. So in this reaction coordinate diagram, we are always starting at the reactants, so that's the left side. products are the end of the reaction. And then the transition state is this high energy state. We can tell based on the location of the reactants and products, and that the products have lower potential energy than the reactants, that this is an exothermic reaction. And then what's happening at that transition state? Let's talk a little bit more about that. We start with two NO molecules where nitrogen is double bonded to an oxygen. In the transition state, the nitrogen to oxygen bonds are breaking. And the nitrogen to nitrogen bond is forming, the oxygen to oxygen bond is forming. And we've learned in the past, breaking bonds requires energy. Forming bonds releases energy. So this graph gives us some information about the energy required to go from reactants to products, the fact that it's an exothermic reaction, and we have one transition state here. We can also label activation energy. That is the distance between the reactants and the transition state, so the difference in energy between those 2 points in the graph. Okay, so there's a reaction coordinate diagram for an actual reaction here. Now, in order for the reaction to even proceed, we need to have two NO molecules that collide with each other. So we're going to talk about collision theory. Reactions occur when reactants collide with each other, but only when the reactants have the appropriate energy and are in the correct orientation. Okay, so many reactions occur in solution. So let's look at the picture on the left right now. RxN is short for reaction, so many reactions occur in solution. So if you increase temperature, molecules or atoms have more and more energy. They're moving around at a faster rate, so that would increase the collisions or the rate of collisions. Increasing temperature increases the collisions between reactants, and that would increase the rate of the reaction as a result, because products would be formed at a faster rate. Now on the right side, this is showing the correct orientation part of the sentence. So if we start with two NO molecules and we're forming N2 and O2, we need the reagents, the NO molecules, to be in the correct orientation where the N molecules, the nitrogen atoms, can bond with each other, and the oxygen atoms can bond with each other. So if they're not in the right orientation, like this example or this example, the reaction's not going to occur. So a few things are needed for that reaction to happen, and the equation on the next slide describes that relationship between frequency of collisions, temperature, and rate of the reaction. So this is the Arrhenius equation. There are two versions. I'll be honest, the one on the right is easier to work with. We will use that one a lot, but we first had the equation on the left. So let's talk through this one. K is still the rate constant. A is a frequency factor. Having to do with collision frequency. This is activation energy. T is temperature in Kelvin. And then R is the gas constant. Notice that we're talking about energy here. So the gas constant, we use the version that has units of joules per mole times Kelvin. So rate constant then is a factor, a result of frequency of collisions, temperature, activation energy. The version on the right side is a y equals mx plus b version. So K is a factor of temperature. So we have this ln of K is the y. This fraction here is the slope, negative activation energy over R. 1 over T is x, and then natural log of A is a constant. So that would be y equals mx plus b. This version is easier to work with. We will use this one more often than the other. Okay, we've got a question, a learning check here. We're going to use the data provided in the table to calculate the activation energy for this reaction. So we have K at different temperatures. Notice that this graph has plotted natural log of K versus 1 over temperature. That is useful for the equation on the right, where we have 1 over temperature as the x value, natural log of K is the y axis. So the slope of this line, well, let's write the equation from the previous slide. Natural log of K is equal to negative activation energy over R times 1 over temperature plus natural log of A. So we want to find activation energy. We are given some data and the slope of that line. That slope has already been provided to us. So the line was plotted based on the information in this table, and then the slope of that line can be calculated using a program. Because I've already given the slope to you, we can go straight to setting the slope equal to activation energy over R. Now I'm going to give you the unit for the slope. It is Kelvin. Let's talk about why that is. Off in the corner here. So if we have activation energy over R, activation energy would be in units of joules per mole. And then R is joules per mole times Kelvin. So if we cancel out joules per mole, we have 1 over Kelvin, which is Kelvin. So the slope units is Kelvin here. If we want to solve for activation energy, we can have activation energy equals negative R, so 8.314 joules per mole times Kelvin times negative 30317 Kelvin. Activation energy is 252,000 joules per mole, and we can convert that to kilojoules just so it's a more manageable number, 252 kilojoules per mole. So by calculating rate constant or measuring rate constant at different temperatures, you are able to determine the activation energy for a reaction. Again, this is because rate constant change with temperature. So using those experimental values, we're able to calculate activation energy. There is a 2-point version of the Arrhenius equation. This is useful for comparing rate constants at two different temperatures. It's also useful for determining activation energy if you know the rate constant at two temperatures. So this version, I believe is in your, yes, it is on your periodic table equation sheet. So again, if you're given information about a reaction where you have rate constant at different temperatures, where you have activation energy and you're missing a rate constant or missing a temperature, we're able to use this to calculate what is needed. So let's do one of those questions. We will use the 2-point Arrhenius equation to calculate the activation energy of this reaction. So this is the same reaction as previous question. To find the activation energy in what we're looking at here, we had to measure K or determine K at different temperatures, plot the data, find the slope of the line, and then use that to find activation energy. To avoid having to plot data and find the slope, we can use this 2-point version. So we have the same data table as the slide, same reaction as that slide, 2 slides back, and we'll use the 2-point version to calculate activation energy. Again, we're avoiding having to plot these data points and find the slope of the line. So just rewriting that equation, we have natural log of K1 over K2 is activation energy over R times 1 over T2 minus 1 over T1. We could pick any two of the data sets. I'm just going to pick the first 2 rows and calculate activation energy there. So we'll have natural log of K1 0.0018 divided by K2 This is equal to activation energy over R, 8.314 joules per mole Kelvin. And then 1 over T2, 975 Kelvin, minus 1 over T1, 850. If I simplify everything on the left side, I get negative 4.577. I'll keep one extra sig fig, 4.579. Units are canceled out on the left. On the right side, I have negative 0.00001814 moles per joule times activation energy. If I divide both sides by that 0.00001814 value, I get 252,302 joules per mole is our activation energy. If we convert that to 3 sig figs in kilojoules, that's again 252 kilojoules per mole. Same value as what we calculated 2 slides back. We get that 252 kilojoules per mole. Benefit is that we've avoided plotting the data points and finding the slope of the line. Okay, so I'd say for the most part, the most involved math that we're doing in this chapter is pretty much done here. So finding rate laws based on experimental data, or using integrated rate laws, or the Arrhenius equation given experimental data. Those are the more intense math questions or math problems that we'd have in this chapter. So the next section, if you need a break, take a break now. We're moving to 14.5 reaction mechanisms. So here we'll define and discuss what a reaction mechanism is. We will write rate laws for elementary steps, identify intermediates, and determine if a reaction mechanism is consistent with the experimentally determined rate law, given some info. Okay, so you all may have seen the Calvin cycle before in your biology class, or photosynthesis before. These reactions occur in many steps. Some reactions occur in one step, but many reactions like photosynthesis occur in multiple steps. So each step is a molecular event where some material is getting converted to something else. Multiple step reactions can be described as a series of elementary steps. So the photosynthesis, if you look at just the photosynthesis reaction, going from first reactants to final products, it can be summarized as one reaction, but it actually occurs in many steps. If we look at the Calvin cycle, we've got multiple steps here. Each arrow is indicating at least one step there. So each singular step is an elementary step, but the whole thing would be a reaction mechanism. Elementary steps have each elementary step has their own activation energy and transition state. So let's say we have a 2-step reaction. We're going to draw what a reaction coordinate diagram would look like. But how this would occur is a portion of the reactant molecules would react to form a short-lived unstable intermediate. Then the intermediate reacts with remaining reactant molecules to produce the final product. Okay, so on the reaction coordinate diagram, we still start with reactants. I'm going to draw a line here. Starting with reactants. Reactants absorb some energy and form a transition state. Then if you have a multi-step reaction, after the transition state, these molecules don't form the product, they form an intermediate. I'm going to label that as I right now. Well, right over here. I equals intermediate. Then the intermediate or intermediates will continue reacting and form another transition state. And then if the reaction is only 2 steps, then the products are formed. So we have 2 transition states, I'll label as TS1 and TS2. We have 2 activation energies. The first one is from reactants to transition state. The second one is from intermediate to the second transition state. So 2 different activation energies, but 1 set of reactants and 1 set of products. Let's write out an example. We're going to use letters to represent molecules here. Let's say we have this information. We have an overall reaction that is AB, so some molecule plus another molecule forms those products. So whatever A is recombines with C, and then B is now left on its own on the product side. And then also let's say we are given these 2 steps. First, AB in the first elementary step breaks apart into A plus B. Then A and C can react to form AC. So this would be the overall reaction that occurs through these 2 steps. So in this case, reactants are AB and C. The intermediate is A, and then the products are AC and B. Okay, I feel like after I explain that, that sounds like a bunch of gibberish. So we're going to do a real example on the next slide where you can actually see a reaction that occurs in 2 steps and how we can get that overall reaction. Okay, let's just do that. So elementary steps, we've talked about, those are the singular steps that happen at once. Multiple elementary steps can form a reaction mechanism. So a mechanism is the sum of all elementary steps, often indicated as overall reaction. So here's a reaction that occurs in 2 steps. Nitrogen dioxide and carbon monoxide react with each other in that step, or in these 2 steps. And we can use this information to write out the overall equation for the reaction mechanism. So first, NO2 and NO2 collide. They form NO and NO3. So let's write that in words up here. Step 1, NO2, or we'll say 2 NO2 molecules collide to form NO and NO3. And then if you look at the second elementary step, an NO3 molecule then reacts with CO to produce NO2 and CO2. And reforms NO2. Okay, so that's a summary of what's happening here. It's kind of like a story, steps to that story for the full reaction to happen. So the overall equation, to write out the overall equation, this is what you will be doing in lots of practice problems. We need to identify what is produced and then used up, or what is used up and then reproduced. We'll actually talk about that in the next section. We cancel anything out that's on the left side of these arrows and the right side. So our first example will be NO3. NO3 is on the left side as a reactant and the right side as a product. So that gets canceled out. NO3 is an intermediate. It is produced and then it's consumed. So it does not appear in the overall equation. Okay, so I wanted to use NO2 or NO3 as an example. Let's look at NO2 now. So we have, I'll use highlighting. We have NO2, NO2, and NO2. There are 3 NO2s in these elementary steps. 2 of them are on the reactant side, 1 is on the product side. So 1 on the reactant side gets canceled out. The other one appears in the overall equation. So we have 1 mole of NO gas. Now if we look at CO, that is the only location I see carbon monoxide. So that remains a reagent. And then that takes care of all of the reagents in these elementary steps. So now we go to the product side. Looking at NO, that's the only location I see NO in these elementary steps, so that will remain. And then same thing with CO2. The last one here, that's the only location where we see CO2, so that remains in the overall reaction. Okay, so we can cancel out reagents and products if they're present on both sides of the elementary step to get the overall equation, the overall reaction. If something is produced and then used up, it is an intermediate. In this case, NO2 is not an intermediate because it is used and then reproduced. So not an intermediate, but NO3 is. All right, now we can describe the molecularity of a reaction and the rate laws. So the number of molecules involved in an elementary step determines its molecularity. So if you know you're looking at an elementary step, we can write the rate law directly from that step. So it has to be labeled somehow as an elementary step. So for example, if we have this reaction here, AB forms A plus B. There's only one reactant molecule, so we call this a unimolecular reaction, or a unimolecular step. And so the rate is equal to rate constant times the concentration of that step. If we look at the second row, we have A plus C forming AC. Main factor here is that there are two reactant molecules. That is a bimolecular reaction. And so rate would be equal to K times concentration of A times concentration of C. Third row, we have again two reactant molecules, but they are identical. This is again bimolecular. And so the rate would be concentration of A times concentration of A, or K times concentration of A times concentration of A. Or in other words, we can just write A squared. Then lastly, the elementary step has three reactant molecules. That is a termolecular reaction. This is pretty rare, but we can still write our rate law. K times the concentration of A squared times the concentration of B. So we can only write the rate laws directly from the reaction equation if you know it is an elementary step. When we were writing rate laws based on experimental data in earlier sections, those reactions are not necessarily an elementary step. So if we don't know if it is, or we know that it is not an elementary step, then we have to use experimental data. Okay, let's go to next learning check. N2O decomposes into oxygen and nitrogen through this two-step mechanism. So for each step, we will determine the molecularity and write the rate law, and then write the overall reaction equation. Okay, let's write molecularity and rate law. I'm just going to make a table to organize this. Step 1, molecularity. Well, we have one reagent there, so that must be a unimolecular. And the rate law for that step would be K times the concentration of N2O. If we look at step 2, there are two reagents present, so that is a bimolecular elementary step. And the rate would be K times the concentration of N2O times the concentration of O. Okay, so we've got molecularity and rates here. Let's write the overall reaction. Again, canceling out anything that's present on both sides. I'll use highlighting again. So let's just start with all the reactants. We have N2O. And then I'm just going to look around and see if I find that anywhere else. And I see it as another reagent in step 2. And that's it. So that tells me that in the overall reaction, we have a coefficient of 2 in front of N2O. Let's look at oxygen, just O. I see it as a reagent, and I see it as a product. And notice we are only canceling out the identical components, or adding together identical components. It has to be the same exact atom or molecule in the same phase. So we can't cancel out O, which I've highlighted in pink, with O2, which is the last product there, because those are different. So because O is present as a reactant and a product, 1 mole each, those get canceled out. And they are not part of the overall reaction equation. Now I'm done with reagent, so I can add my arrow. Let's look for N2, the next product here. I see that present as 2 moles in the product. And then our last one here is O2. And that's the only location where we see O2, so that will be a product as well. So the overall reaction is written there. We have rate law and molecularity for each step. Okay, I think with this you can do quite a lot of the homework, even into the chapter 14 part 2. I'm going to stop the video here. We'll do the next part talking about rate determining steps and the next learning check. When we get back to class, we'll finish chapter 14 and start 15 at that time.